right, let's pick it up. The next few example problems, we did parts A, B, and C. We're on to part D. Grab, not what I meant to do. Let me grab my other camera. Okay. Part D here, we're looking at the limit as x approaches infinity, and our function is the sine of x. Now this is interesting. The sine of x. Hopefully you're fairly familiar with the graph of sine x, right? It's got that oscillating wave feature to it. If you did that, you think, okay, sine, without being too precise here, maybe that's like pi, 2 pi, 3 pi even, right? It starts at 0, it comes up, it goes back down through pi, comes down through 2 pi and up again, and it keeps doing that cycle over and over. So as x tends to infinity, as we go out, in order to have an answer for our limit, the function needs to be approaching a single y value. It could be that y value is, infinity or negative infinity, but if it's a finite number, it would have to be like leveling off if there's a horizontal asymptote. That does not happen here with the sine of x. It's always stuck between +1 and -1, but it takes on every single value between them over and over and over again. It never tends towards a horizontal asymptote. So because that's the case, the answer to this limit is D and E. It does not exist. Let's make that really clear. It does not tend to one y value as x goes to infinity. Okay, hopefully that's clear. Let's take a look at the next one. Kind of similar. Here we're going to negative infinity. We've got the sine of x over x cubed. And now you might say, like, based on what we just did in part D, hey, if we're looking at anything that involves the sine of x and the limit here with sine of x was D and E, wouldn't this answer be D and E as well? Not so fast. Because of that x cube, that's going to change things significantly. If we think about the sine of x, we know that is going to stay between -1 and +1. Right, and we're going to negative infinity, we're going back the other way, but we get it. It stays between -1 and +1. What happens to x cubed as x goes to negative infinity? Well, negative infinity cubed would stay as negative infinity. The negative cube stays negative, it's infinity. So think about this. The numerator stays between -1 and +1. The denominator, it's negative, but more importantly, it's getting really, really big. So you're dividing by a bigger and bigger and bigger value. Even though the numerator never stays put, it never goes to a single value, because we're dividing, that graph as we go out to negative infinity is going to be shrinking, 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 because that denominator just takes over. So this answer will be 0. Check out the graph. It's kind of interesting. It kind of does that wave, but as it goes further out, it shrinks really fast, and it just barely hovers above and below the x-axis, which does act as a horizontal asymptote. Okay. Now let's take a look at the next set. These are all kind of similar. We've got x approaching infinity, 2x minus 1 over 7x plus 3. For parts D and E, it was more like we were kind of just considering what happens to the numerator and denominator sort of separately. There wasn't any algebra to do or simplification. We're just kind of thinking about the graphs and stuff like that. Very different here for parts F, G, and H. So starting here, let's see what's going on with part F. 2x minus 1 over 7x plus 3. If you were to kind of think about the numerator and denominator separately, you think, okay, like if you plugged in infinity, what would happen? Well, 2 times infinity is infinity minus 1, right? Still infinity. The denominator, 7 times infinity plus 3, you would get infinity over infinity. When you have infinity over infinity, lots of things are possible. What this limit will end up equaling depends on the specific functions that are involved. It could be that infinity over infinity leads us to an answer of infinity. It could be that infinity over infinity leads us to an answer of 0. Or it could be even some other finite number right between 0 and infinity. We don't have an answer yet. So here's what we'll do. We're going to use algebra to rewrite this rational function. And rewriting it, we'll be able to take advantage of kind of that aspect that we thought about at the beginning, like that 1 over x, like headed towards 0, sort of a thinking. Here's how we're going to rewrite this. We're going to divide each term by the highest power of x in the denominator. So we're going to look at the denominator. We're going to recognize, hey, the highest power of x is just x to the first. So let's divide all 4 of these terms by x. And that's going to put us in a really good position. Dividing everything by x won't change the value of the function, right? But it will allow us to take this limit. So if we divide by x, let's see, that's going to be 2 minus 1 over x. And down here, 7 plus 3 over x. It's still all equivalent to what we had at the beginning. Now, when we take this limit, if we look at each piece one at a time, the limit as x approaches infinity for 2 is just going to remain as 2 because that's a horizontal line. But now the 1 over x goes to 0. The 7 remains a 7. The 3 over x goes to 0. And we've got our answer 2/7. That's kind of cool. It turns out it's this finite number, right? Somewhere between 0 and infinity. And it turns out it's the ratio of those highest powers, those ratios of the x terms. Okay, very nice. Let's take a look at part G. The limit as x approaches infinity. 2x minus 1. We're just going to change this slightly. Let's make it 7x squared plus 3. Now we got this rational function, right? If we tried to plug in infinity, it would still be infinity over infinity. But our answer this time is going to be different. What are we going to divide everything by? Well, the highest power of x in the denominator is x squared. So we're going to divide each term by that. Say, okay. So 2x over x squared is 2 over x minus 1 over x squared. Then the 7x squared divided by x squared is 7. And finally, plus 3 over x squared. You might think, why do we choose the highest power of x in the denominator? Because we want to pick the biggest thing we can without causing the denominator to go to 0 when we do the limit. So if we divide by x squared, I know we'll at least have a 7, and this whole thing down here won't go to 0. It's okay if the numerator goes to 0, but not the denominator. Okay, so what happens? Well, if we look at the limits one at a time, 0 minus 0 over 7 plus 0, 0 over 7. This final answer is 0. It turned out, because there was an x squared in the bottom, that the denominator was going to infinity much faster than the numerator was, right? Infinity squared is, well, there's still infinity, but the numbers are much bigger, right? And here's kind of why it's dangerous to think about it as infinity squared. X is approaching infinity. Think of it more like the x values are getting bigger and bigger and bigger. So maybe like x equals 10 versus x equals 100 versus x equals 1,000. Well, 1,000 squared is much bigger than 1,000. And every time x gets bigger, that gap between the squared and the original gets larger and larger and larger. So that denominator is running away towards infinity faster than the numerator is. And because the denominator is getting bigger so much faster, this whole thing ends up going towards 0. It's like the denominator wins, if you will, the race. Let's look at one more of these, part H, the limit as x approaches 0, 2x to the 5th minus 1 over 7x cubed plus 3. In this case, we've got the power of x being the larger in the numerator. Let's see what happens. We're going to divide everything by largest power of x in the denominator, x cubed. What's that going to leave us with? Well, dividing here by x cubed is 2x squared minus 1 over x cubed over 7, because we don't want this to go to 0, so we limit ourselves at that. 7 plus 3 over x cubed. And now taking this limit, we can see, x going to infinity for 2x squared, that's going to infinity, minus 0 over 7 plus 0. We've got infinity divided by 7, but that is infinity. Okay, hey, let's take a look at some graphs. We see here, that higher power in the numerator. What happened? Well, the infinity cubed, or x value, is getting bigger. If you go to the 5th power versus the cube, I should say, well, that 5th power is going to run to infinity faster than the cube will. And so it's like the numerator wins out, if you will, and it gets to infinity. Some quick graphs. Let's take a look back. We had 7x, it was 2x minus 1 over 7x plus 3. And so there we can see, yeah, there's a horizontal asymptote. It's not quite clear, but that happens at 2/7. And as we go out to infinity, our horizontal asymptote. Okay. In the next problem, we changed this to x squared. When we did that, really changed the graph. And now we can see, yep, it's really staying close to 0. So as we go to infinity, it's headed towards 0 now. And then that last example, we had this. Oh, that's kind of an interesting graph. 2x to the 5th minus 1 over 7x cubed plus 3. And now as x goes to infinity, the y value is shooting up and up and up to infinity. What did we have just prior? Oh yeah, the sine. We got to do these. Sine x, okay, right? That's a DNE. But what if we make it over x to the third? Interesting. Now there's a vertical asymptote at 0. And yep, there is some oscillation, but it's really small. So we can see those, it's still passing through the x-axis. So it's above, it dips just barely below, but then it comes back above. Or maybe that's even like a minimum value. And then it kind of goes back up. And okay, now it's gone through 0 again there at 2 pi. And then it's going to end up falling back. It peaks right here and then it crosses through again at 3 pi. So it's just barely waving back and forth, but definitely going to 0. And I think we actually looked at it in the negative direction. There you go. Okay, let's stop this video here. We got a couple more coming up.